Hi everyone, so welcome to this week 11's lectures on the course on linear systems theory. I am Ramkrishna from IIT Madras. If you have survived this course till week 11, I think you are doing pretty good. So just a very quick recap of what happened over the past 2 or 3 weeks was, at least from the design perspective, we had formulated design problems as certain, say, pole placement problems, or we also at some point of time asked ourselves the question, what if the states are not completely measurable? Then we had an equivalent observer design. We also looked at simultaneous controller and observer design, and so how a design of a controller doesn't really affect what is going on in the observer design, and vice versa. So these can be treated as independent problems, and how also towards the end we saw that the observer dynamics should be faster than the controller dynamics for obvious performance reasons. Okay, so what we were interested in? We were interested in, one, stability; second, performance in terms of placing the closed loop poles at desired locations, and of course at times when we required an observer design, we actually also followed the procedure of designing the observer. And starting from the definition of controllability, right? So loosely speaking, so the control definition was, can I start from any point in the state space and come back to the origin with help of some unconstrained control? I was not really interested in what is the control effort required or how much time does it really take. I was just happy saying, well, it should reach from point A to point B in some finite time, right? And also an unconstrained control input. So we were only interested whether or not the system is, say for example, controllable. We never talked about what is the cost of the control, in what. So can I say, okay, with a control restricted to some quantity u bar, can I reach from point A to point B in, say, some 5 seconds, for example, right? We never really talked about quantifying those quantities, right, of the inputs, the time, and so on. So what we will today do is to look slightly beyond just pole placement, or just beyond looking at stabilization kind of properties, or beyond looking at just a control problem as just u equal to minus kx, such that the poles of the closed loop system are at the appropriate locations. So we will do something slightly different today, and of what is called as an optimal control. So what is a good control law? A good control law is something, is an expensive control law a good control law, right? It's like if I were to draw an analogy to check, okay, what is a good car for me to buy? Okay, then you just maybe just out of curiosity just ask Google, or you ask Alexa, for example. She is also quite competent these days. So what is a good car? And that in sometimes is also not a well posed problem, because you don't really specify your requirements of why do you need a car, what is the cost that you can afford, and so on. It's also looking in a different way. If I say I get a salary per month, I want to maximize my savings, I also want to maximize my comforts, right? So what is a good solution? So if I say, well, I want to maximize my savings, then I should not spend at all. Or if I say I want to maximize my comfort or luxury levels, I should not save at all. So this is like, in some sense, a contradictory problem, right, of maximizing my savings versus maximizing my comfort levels. So what does that mean in the control sense, right? Can we actually solve problems like this when we have a conflict between good performance plus some constraints which occur to us? Okay, so what are the control problems that we typically encounter, or say, so one is what we call as the state regulation problem, which is to keep the state x near 0, right, so to speak. So what is the aim of the controller? Aim of the controller is to design a control law which takes the state of a plant from some non-zero values to the zero state, equilibrium for example. Now, well, why does this actually occur? Why do I even need to design a controller? So, if I am at the equilibrium, I will always be at the equilibrium. So, what could cause the state to move away from the origin? There could be disturbances, there could be external perturbations. Say if I am looking at a power grid, a sudden change in load patterns might actually trigger my system in such a way that it will move away from the set point. Or if I am looking at IRCTC website, a sudden a booking pattern might take my system away from my set point, so to speak. So, we can also similarly look at not only state regulation, but output regulation, where the objective would be to keep the output near 0 or so the 0 is that I do not want to really drive the system to a 0 output, but some kind of a reference value which I set, and usually you can also talk of it in terms of the error being towards 0. Okay. Now, the third thing could be looking at a tracking problem, right, where I can make the state follow, or even the output in some case follow a desired trajectory. Say I want to design a solar panel, then it seems, so if I would maybe face it at the east in the morning, towards the end of the day I may not maximize the output of my solar generator, right. So, I have to really track the position of the sun, and this has been kind of a very interesting and well studied problem in control literature, or even from power engineering perspective, right. So, these are typical control problems that we encounter. So far we are like, okay, can I design a controller u equal to minus kx such that poles are blah blah blah, performance is blah blah blah, and so on. Okay. So, when I look at a little further, yes, I can design a controller, but now I need to answer a little more questions, right. So, one question would be, well, the main objective here, if I look at an optimal control, is to design a control signal that minimizes a certain cost, right. At the same time, does it maximize a certain performance index, and the plant could have some physical constraints, right. Say for example, if I drive a car, I know that I possibly cannot go beyond say 150 kilometers per hour or 200 kilometers per hour. It just comes with some kind of a physical constraint. So, even though the car can move as a controllable analysis would suggest that the car can go from point A to point B in some finite time. Okay. Now, if I say, can I go from say Chennai to Delhi by my car in say 2 hours? Well, that's a difficult question to answer, right. The answer may always not be possible, because my car is physically constrained by its maximum speed. Then in most cases, I also want to maximize a performance index. Performance index could be in terms of say if I go back to the web server problem which we had in the week 1's lectures, can I serve maximum requests per second, right. And not only that, can I also serve requests as fast as possible? There was a contradiction also in that particular problem, right. And then of course, I want to minimize the overall cost, right. So, ideally I would want maximum performance at 0 cost, right. That is like the ideal situation. Well, but unfortunately that does not happen. So, is there something that will help us a bit in this? Okay, what could be other examples? Right? So, something which is being talked about everywhere is about soft landing, so to speak. Okay. So, okay, I will not tell you why we couldn't get to a soft landing. Okay, we will leave that for somebody else to say. But if I just looking at, say, just to draw some parallel between what I learn here to what I actually see on TV each day, right. So, one is if I look at a soft landing of a spacecraft, I am just saying it is simplified, right. We can't do better than those scientists. So, what is the primary task? The primary task is to land at a specific position with specific velocity in finite time, okay, while minimizing, well, the fuel consumption and minimizing the time. This could be one of the cost or the performance index. At the same time, there could be physical constraints, that the thrusters might have a limited capacity, okay, and so on. and there could also be upper bound on the maximum attainable speed, right, for whatever reasons, right. For example, if I look at a current carrying capacity of a transformer or a voltage rating, it's not necessarily due to the conductor there, but it's mostly the properties of the insulator that kind of motivate that rating, right. So, these are essentially physical constraints which come with the system. Okay. Now, of course, there are another physical constraint, you cannot go below the ground, right. This is kind of obvious, but this is a real time physical constraint. Okay. Now, what do we need to solve such problems? It's kind of fancy to talk about these problems of what they call also as soft landing and so on. What do we need to solve such problems? Well, from our control engineer's perspective, we need a few things, right. I need some few information. First is I should know the plant dynamics as closely as possible. I need to know what is my performance specification. Okay. For example, my performance specification as a teacher should be on my teaching abilities, but not my football skills or lack of that, right. So, given a performance specifications, boundary conditions, right, what are my limitations of what can be worked out, what cannot be worked out, right, and then of course physical constraints of the system, right. So in general, if I were to look at formulating this problem mathematically, so all the time what we were interested is, given a physical system, can we write a model of that? A model was a mathematical abstraction of the system in terms of linear ordinary differential equations mostly in this course, right. So, from that model, can I derive a control law and then put it back to my original physical system? That was my very straightforward design procedure said in a simplified way. Okay. So, let us say one of the more general forms of cost function. I think different books will start with different motivation, because okay, we are not really doing an optimal control course here, but this is just a little introduction to optimal control. You are just like not even like scratching the surface, you are just maybe watching the surface a bit from distance. Okay. So, what am I interested in, right? So, what does this entire integral here mean, right? So, what is okay, let's analyze each of these terms a little in detail. Okay. So, first I have some difference here, z minus y, z minus y, something to do with the inputs and something which has some Tf here, right. So, we will just analyze what are each of these terms. Okay. So, let me say that the first term in general could correspond to some kind of a tracking error, right. I mean, if I just want my state to go to 0, then it will just be that okay, I am just looking at x minus 0. So, this is my reference, this is my actual and so on. So, this is something to do with the error. Okay. Error, some term q here, I will tell you what this means. This is the input, again some matrix R here. Okay. So, we will come to this term a little later. Okay. So, first is the first one. The first is the error weighted matrix Q. Okay. First is that well, usually you would want, or we would want the error to be small. Okay. So, this usually has the form E transpose. Okay. So, lots of people use also this 1 by 2 just because when you differentiate the 2 will go away, but okay, without loss of generality you can also remove the 1 by 2. So, I am looking at a signal which is of this form E transpose T Q E of T. Okay. Now, typically, so this could also have some kind of interpretation in terms of the energy of the signal. Okay. Now, well, this should always be non-negative. Okay. So, this is a little approximation when say Q is say identity, for example. Okay. This quantity is always non-negative, and therefore, the nature of Q, and sometimes it could also depend on T, is such that it is positive definite. Okay. So, what do we have to pay attention to? We may have to pay attention to large errors, and they are not usually permissible. Now, second thing I have is the control weighted matrix. So, what in the first case what we know is that the error weighted matrix Q should be positive definite, right. So, we just get some kind of a quantification of the error, right, and then that the error should be small and so on. Okay. So, the control weighted matrix, it also has a form like this. So, you have half U transpose R times U. Okay. So, what this means is that, well, if R is typically greater than 0, that one has to incur a higher cost for a larger control effort. That is kind of natural, right. If I want to put in more control effort, I would incur a natural a larger cost. Say if I want to have a car which goes at say 250 kilometers an hour, I would possibly not get that for a price of a Maruti Alto, for example, right. Okay. So, and then the control signal, right. The control signal, as I said earlier, is usually unconstrained, even though while in our basic analysis we kind of assume that there is a, let's see, well, if there is an unconstrained control, can I actually go from point A to point B. Okay. Now, what is the conclusion from this 3 points? The conclusion is that we would like to keep the error small, okay, keep the error small and not pay a lot for control, right. So, my error should be small, but it should also not incur a large cost on me. Okay. And then last we have what is called as the terminal cost. So, that is taken care of by this term. Okay. So, the terminal cost is to ensure that the error at the final time is as small as possible. Say I want to go from point A to point B in some TF. So, where am I at how far am I from the desired performance objectives at the final time is what this quantifies. Okay. And as usual, again this matrix Q of F should be positive definite. Okay. So, in general what I would like to then say that, okay, I want to keep error small, not pay a large cost, and therefore and at the same time also have the error at the final time is as small as possible. Now, can I design a controller which achieves these objectives? Okay. So, again how my controller look like? Controller will just look like this, very similar to what we had previously. Now, what is a good K? Okay. Now, is there a standard solution to this? So, what will be important here is how much importance I give to each of those quantities. For example, I may want to reach point A, from point A to point B in a shorter time, which means I am willing to pay longer, right. So, I am willing to pay a larger amount of money. Okay. And on the other hand, if I have constraints on the money of going from point A to point B, I am okay to go by a slow moving transport or a public transport, for example, right. So, I fix those weights, things via these terms, and then decide how am I going to achieve my control objective given those certain constraints. A solution may always not exist. For example, going from Chennai to Delhi in 2 hours with my little car, it will not exist, right. So, these are possibilities that we could encounter. Okay. Now, most books will talk of a little simplified cost function in this form, right. So, we will start just with something which looks like this, right, where J is X transpose Q Qx, U transpose RU remains the same as before. So, first is, okay, minimize the time, that is also, and also at the same time minimize the energy, right. So, as usual, x transpose q x model the energy of the plant, and u transpose u models the control input, and so on. Right, a little general thing that we that most books would. So, we are here talking more like, say, a problem where I am looking at some kind of a state regulation problem where I just want the states to go to 0. Okay. Okay, and then similarly, I will have some kind of a terminal cost. The cost is the cost of not reaching the desired position at the terminal state, and as usual, I want this to be as close to 0, or x t to be equal to x desired, at least as closely as possible. Okay. So, we start with a bit of an assumption that, okay, sometimes the terminal cost is assumed to be 0. So, what we start now first is a finite horizon problem, where I know that I want to reach from, say, a certain initial time and a certain final time is fixed. Okay. Right. Okay. So, what is the problem here? The problem is that given a linear system x dot equal to a x plus b u with some initial state, determine the control signal u that minimizes this particular cost function. Okay. Now, minimize this cost function. So, what is the observation here? First is, look, I am looking at 0 to t finite horizon problem, right, and then I have something which models the state cost, something which models the control cost, and something which models the terminal cost, right. And what we will see, and that, okay, there are multiple ways to solve this problem. So, I will present you 2 or 3 ways which you will regularly encounter in some textbooks. There might be more ways to that. There are lots of detailed analysis, but we will try to get for ourselves a good understanding of what is happening here, right, through 3 different methods, and you can follow whichever method you want, and all methods give me the same solution, right. Okay. So, first is, let us start for a case which may possibly not have a terminal cost. So, which means I have the cost function, which is also sometimes called as the value function, written in this following way. Okay. Should be okay. So, first is, okay, let me call this my cost function or the value function, right, and let us say x of t is z for all t between 0 and capital T. Okay. And well, you can see that from here something which is obvious is that the value function or the cost function has some kind of a quadratic form, right. Say transpose p depending on times p depending on time t times z, and this is also symmetric, like it's a straightforward computation from here till here. Okay. So, the value function here computes the cost incurred due to the use of the control signal from t to t with some initial condition given x t equal to z, right. Okay. So, we start with x t equal to z. Let u t, let me say that it is let u t be a constant function over the time interval t to t plus h with some very small time h, right. And within this interval I can write x t plus h in the following way, a little Taylor series expansion, right. X t plus h is x t plus h x dot. Okay. So, this is kind of obvious, and what is the state during that time? The state is z and the input is w. Okay. What is the cost incurred during that time? Well, the cost incurred during this period is the following, set x from t to t plus h, right, x transpose q, again u transpose r times u, which can be loosely approximated to this. Okay. Again, this is just a little time interval from t to t plus h. Okay. This should again be easy to verify. Okay. Now, okay. So, let's without reading the steps, let us actually try to derive all these things, and I will come back to the explanations again. Okay. Now, first to simplify the value function v t of z. So, what was v t of z? Starting from t to this terminal time capital T, x transpose q x plus u transpose r u dt. Okay, this I can write as two parts, right? One is an integral starting from t to t plus h with having the same things inside, x transpose qx u transpose r u plus the term integrated from now t plus h to t with the same thing in the bracket. So, what will this mean? This will actually be the value function v computed at t plus h with x at t plus h. Okay. So, this is just I am just using the definition of the value function. Okay. Now, from this approximation here, I can rewrite this as z transpose qz plus w transpose r w times h plus v t plus h. Now, again go back to this expression, right? X t plus h is just a simple expansion would tell me that this looks something like this: z plus az plus bw times h. Okay. Now, let us see what this thing looks like: v t plus h z plus az plus bwh is okay. Now, what is v like? V is like this. Vt is a quadratic in p and z. So, this will be z plus az plus bwh the transpose p now at t plus h, right. So, that is where we start from, right, times z plus az plus bwh. Okay, I am not doing anything special here. I am just writing Vt, right, this for this particular V with this particular h, where this particular x, where the x is approximated as this function, right. Okay, so I will okay. So, what is the next step? So, this will remain as it is. P I can again further approximate as P of t plus h times P dot of t, okay, with this guy coming and sitting here again. Okay. Now, this can be further approximated as z transpose P z plus, I will have a bunch of terms here, az plus bw transpose p z plus z transpose p, again p is again depending on time, a z plus bw plus z transpose p z with a p dot, right. So, I am only taking the terms which have a common factor of h, and then you will have something of h square, which I will ignore, because h is like really small, right. So, I can ignore these terms. So, okay. So, where are we now? So, we started with computing, simplifying the value function. I said, okay, I will first integrate from t to t to h, and then I will have the remaining term over here, which is approximated like this, right. Okay. Okay. So, where do I go from here? Okay. So, this Vtz can now be written in the following way. So, the approximation of it, so I am just taking this term plus what I derived over here, which is equivalent to this. So, I will have a bunch of things here, z transpose pz plus all the terms with a common factor of h. Okay, so, there is, so what we will add here is that this term and this term also have a common factor of h. So, they will just go here, right. So, this term will be as it is, z transpose pz. So, whatever is in this big bracket here will have two additional terms, this one and this one. Okay. So, then this is how it will look like. Okay. Now, what we want to so we want to minimize this cost function over what? We want to find the minimum u. Okay. So, what is the u here? So, I am looking at minimizing it over w. So, I get the optimal w. Okay, so small w. Okay, just a function in one variable which I want to minimize. I just take the derivative, equate to 0, and this is what I get. That the optimal control w transpose is minus r inverse b transpose pt times z. Now, what do I have now? So, once I have w, I can now get a state feedback control which is of this form. Okay. U is, so in general, right, if I look at, so for a small w it looked this way. So, what will a general u look like? This is u, this is minus k which varies with time times x, right. Okay. Now, what do I know from here? I know what is r because I fix the matrices here, or I fix the weights of how much, say, constraints I have on the input and how much constraints I have possibly on the state. Okay, right. So, I know this p b is given to me, I know x, right. So, what is unknown here is this term p. Okay. Now, to find this optimal input which depends on p via this relation, I still need to solve for this p of t. Okay. Now, how does this look like? Well, this can be solved by substituting for this. So, the u which was k x t or w which was this k times z, I can put it back here. Okay. So, what does that give me? Right. Okay. I will just skip the computations, but what will that give me? That the equation now simplifies to something like this. Okay. Now, this is usually called as the Riccati differential equation for the LQR problem. Okay. So, where did we start off with? We started off by a system dynamics x dot equal to ax plus bu with some initial condition. We wanted to determine a control input that minimizes a certain cost. Okay. Now, we know that, well, the solution in the absence of this guy, we know that the solution V t is given by this matrix differential equation. Okay. Now, this implies that the solution to the original problem can be found by solving for this equation backwards in time for p 0 with final condition p t equal to q f, right. So, that is what so now I can look at what my terminal cost looks like, right. So, I know this p t is q f and I can actually solve for it now backwards in time. So, once I know this, it becomes a little easy for me, right. So, I can just substitute for that p over here. Okay. Now, this p is again this u of t which is time varying will be k of t times x t and so on, right. So, now what I know is that to get this value of k which is depending on time, I need to solve for this unknown p via this Riccati or via this matrix differential equation, right. So, that is a little basic building block to what we are up to here, right. How do I solve the optimization problem or the optimal control problem? Well, that turns out to be coming from a solution of the matrix differential equation. It's something analogous to the matrix, the Lyapunov matrix equation that we had, A transpose P plus PA is minus Q. But does the solution always exist or not? This depends on whether the system over there was stable or not. It will also depend here whether the system is actually controllable, or can I actually, the solution is does not always exist, and we possibly will see problems also where the solution may not exist. Okay. The next thing which most books will talk about is the infinite horizon problem, in a way that, okay, what will happen when I am looking at the infinite horizon problem is that the final time is infinity, right. So this is the case of infinite final time, okay, and that TF is infinity, okay, and then the final cost term may not, okay, this may not be, may not have any interpretation, may not have any realistic sense. Okay, since we are interested usually in solutions over finite time, and just therefore QF in this case must be equal to 0. So, we are solving now for the same problem with no final cost and the cost j going from 0 to infinity. Okay. So, in this case the value function or the cost function is simply quadratic. It will now be independent of time because, well, there is nothing really associated here. Okay. Now, the problem now turns out to be kind of pretty simple now. So, I am just looking now at a solution. So, instead of a matrix differential equation, I will just have some kind of a linear like looking equation, or well, maybe not, right. So, I am just having maybe a nonlinear equation here, there is no differential term here. So, the solution that will give me the optimal control law is minus R inverse B transpose P times X, where P is now solution of this equation number 12, right. And what is important here to look at is that the state feedback controller, that the gain K here is constant throughout, whereas in the previous case the gain K over here was varying with time because of the dependence of P on time, right. So, that is a little distinction between the infinite horizon problem. And okay, so much of the textbooks will first start with the infinite horizon problem. So, I just do a little reverse, right. So, what I did so far was what is also called as the dynamic programming approach. So, if you look at Ogata, he will have a different method which I will shortly tell you is in the following way. So, consider a linear system, x dot is ax plus bu with some input that we need to design, and in such a way that the matrix K minimizes this cost function or the performance index. Okay. Now, what do I know? Okay, let us write down the steps here. So, what is given to me is again x dot is ax plus bu, and I want to minimize or find a control law u equal to minus kx, which minimizes the cost functions defined from 0 to infinity x transpose qx u transpose r u, right. So, the times dt. So, this is like the linear quadratic regulator, that is where the name comes from possibly. Okay. So, this is the control law, right, and then what do I have as a closed loop system looks something like this: x dot is a minus b k times x, right. We have seen this already a lot. Okay. Now, it will be safe for us to assume that this is stable, right, else there is no point designing this controller. So, let us assume that a minus b k is a stability matrix, okay, and therefore, the cost function now j looks like this, x transpose q x. Okay, sorry, so x, this also means transpose, this also means transpose. So this is x transpose q x plus u is k x. So I will have x transpose k transpose r k times x with dt. Okay, so this is of the form 0 to infinity x transpose q plus k transpose r k x dt. Okay, now let's do some tricks here, right? So let us set this number x transpose q plus k transpose r k times x is minus d over dt x transpose p x. Okay, now, okay, so what do we know, right? So this x transpose q plus k r k x is, okay, just differentiate this and get the following. So this is minus x dot transpose p x minus x transpose p x dot, sorry, x dot here, and this will look like this, minus x transpose a minus b k p plus p a minus b k with a transpose here. Right? Okay, so this is something what we had also for the Lyapunov equation, right? Now what do I know? That a minus b k is stable, right? And therefore, given a matrix q plus k transpose r k, now this is because q and r are greater than 0, this is also greater than 0. For this q, well, I should be able to find a p such that a minus b k transpose p plus p a minus b k. So some equation, some Lyapunov equation like this holds. Okay. Okay, now what is to be found out here while minimizing the cost function is, does there exist a p which satisfies the solution given a certain optimal k. Okay. Now how to evaluate? Or what is the p or what is the appropriate input? So j here is now 0 to infinity. Now from here, right, I just do a substitution. So j was x transpose q plus k transpose r k times x, dt was x transpose p x 0 to infinity. This is x at infinity. There will be a little minus sign here because of the minus here. Minus x transpose infinity p x at infinity plus x naught p x naught. Okay. Now since a minus b k is stable, this will go to 0, and what I am left is j is, sorry, x transpose p x 0. Okay. So this means that I can find the performance index j in terms of the initial condition x naught which is given to me and p. Okay. Now the next step to the solution is the following. So because r is greater than 0, one can always write r as t transpose t. Okay. Now again t is a non-singular matrix and so on, and therefore I can write down my Lyapunov kind of equation which is like this, right? A minus bk transpose p plus p a minus bk plus q plus k transpose t tk equal to 0. Okay, where does this come from? So there is a where exactly here. So for r I just substitute r equal to t transpose. Okay, so next what do I do is I just write down from here till here, right? I am just expanding terms, and minimization of these terms, right, again with respect to k, right. So this is what I am finding. What is a good k? This requires that this particular quantity be the minimum. Okay, since the last expression or once we have so the minimization of j with respect to k, which means we may have to minimize this term. Okay, and this occurs only when, look at this, right. So I have x transpose, I have something here with the transpose, something here, and x. Okay, so this is possible if and only if this term here goes to 0. Okay, and because this expression in general will be non-negative, because I have something like something with a transpose, and this will always be non-negative. So the minimum value here is only 0, and this 0 occurs when the term in the bracket becomes 0, which essentially means that tk is something like this. Okay, now I can back substitute and get a good looking value of k, which is r inverse b transpose p. Okay, let's keep this in mind. R inverse b transpose p is what we also had here. This was my k here, right? R inverse b transpose p. Right. So therefore now I have the optimal control law, which is of this form, and so again the unknown here is this matrix P. Again, how do I find this P? Well, I have this expression for k. In addition, I also have an expression which looked something like this: A minus bk transpose p plus A minus bkp A transpose p plus, I think it should be a p here, sorry. This was equal to minus q plus k transpose r k. Now substitute for this k in this equation, right? So I am just using this equation again, or this equation, right? Substitute for k, and what we end up is that this reduces to solving this equation in P, right? So this is called the reduced matrix Riccati equation, or also the algebraic Riccati equation. Okay, so this is the second method for solving. So in the next class, what we will also do, or in the next lecture, to look at another method of solving the same problem, same optimal control problem, and I will give you a brief introduction of the solvability of these Riccati equations. Under what conditions do I get the solution? Are there simplified methods to check whether or not there will exist a solution? How much is controllability important? How much is stabilizability important, and so on, right? So that will come up in the next lecture. Thanks for listening.